Hello everyone. In this video we are going to see how we can derive different hydrological parameters and what are different techniques used to measure those parameters. Now let's start with the overall contents of this presentation. The first we'll talk about precipitation, initial losses, evapotranspiration, surface runoff, infiltration, and their measurements. So how we can measure these different hydrological parameters. Okay, and then next is to convert the point precipitation to aerial precipitation. So we measure precipitation at some locations. So they are called the point precipitation. How we can convert that to the catchment scale. Okay, so that's conversion from point to aerial precipitation. How we can estimate evapotranspiration, estimation of initial losses. So when rainfall occurs, uh, all the rainfall will not be converted to runoff. There will be some infiltration, there will be some losses in terms of interception and initial depression. So we need to include that in our calculation. Okay, so how we can estimate those losses. So we'll talk about that. And finally, we'll use the IFD data from ARR. So intensity, frequency, duration data from Australian rainfall runoff to estimate design rainfall. So we'll see how we can use the ARR software to derive the IFD data. Now let's start with the precipitation. Precipitation refers to any form of water that falls from the atmosphere to Earth's surface. That can be rain, snow, sleet, and hail, or any other forms of moisture. And the precipitation is measured using rain gauge, which collects and measures the amount of water that falls in a given area over a set period of time. So normally we have the standard uh, measuring equipment, and we measure how much water is in that the collecting equipment divided by the surface area. That will give us the depth of rainfall, and which is the rainfall. Now, the precipitation can be highly variable both in time and space. So rainfall is variable in space and time due to several factors. For example, due to geography, due to topography. So in high mountains, you may receive more precipitation and the lower area. Similarly, the latitude, winds, time of the day, season, climate change, distance from ocean, all these affects the precipitation. Now, one of the methods to estimate or measure the precipitation is using the rain gauge that I mentioned before, but there are other methods like using the radar and using satellites as well. These tools can help to determine what is the intensity of rainfall and what is the duration of rainfall at one particular location. Now, rainfall depth is generally measured in terms of a millimeter, and rainfall intensity is measured in terms of millimeter per hour. So there are two things that we need to remember: depth of rainfall and intensity of rainfall. So depth of rainfall means the amount in terms of millimeter, the depth of rainfall, whereas intensity is that depth per unit of time. So that is millimeter per hour. Now, another thing we need to when it comes to design of different water infrastructures, we use frequency, duration, and intensity of rainfall. The relationship between the frequency of rainfall, so how frequent the particular rain occurs, uh, for example, 100 millimeter per hour of rainfall, how frequent that occurs, right? So, and the duration of rainfall, right, and the intensity. So these three are quite important parameters. So when we design our water infrastructures, we need to decide what should be the frequency of rainfall that we use, what should be the duration of rainfall which we should use, because if the duration of rainfall is 2 hours or 5 hours or 5 days, they will produce different kind of rainfall based on the historical data. So we need to think about the frequency, duration, and intensity of the rainfalls. Now we know that the intense rain can cause more surface runoff, right? So when the intensity of rainfall is high, it can cause more the larger surface runoff, and it leads to river floods and soil erosion. And this can be particularly problematic in areas with poor drainage, steep topography, and impermeable soils. On the other hand, if there is a light rainfall, that means it has more time to infiltrate uh, inside the ground, and that will help to recharge the groundwater and also support the vegetation growth. This is an example of tipping bucket. Okay, so when we measure the precipitation, so this is at the top, so this part goes here, right? And then we know the area of this bucket. And what happens is when the rainfall occurs, uh, it falls inside this bucket and then eventually starts to drop at the bucket here. So you can see here there are two buckets. The first bucket is on the left hand side and the second one is on the right hand side. And when the water starts to drop here, the weight of this part of the bucket starts to get heavier, and eventually at some point it will go down and hits the sensor here, and it will count as one. Okay, and then when it hits here, the other bucket goes up, and then that starts to collect the rain. And then again, when that certain volume reach when that certain volume reaches, and then it goes down, and here's this another sensor here, and it counts two. And same way it counts the number of times it is the sensors are hit by these buckets. And then because we would know the volume of the bucket, then we can calculate what is the rainfall amount. And we also will be able to see how frequently or how fast these buckets are being hit. And then from that, we can see and calculate the intensity of rainfall. So there is a standard of how we and where we put our rain gauge. So we can't put any direction. So we need to have some kind of standard. And so, for example, when you draw the 30-degree angle, and there could be building or trees, and if the height of a building or tree is h, then the distance from the rain gauge station to that point should be 2h. So this is a kind of um, uh, uh, the standard that we need to use when we put our rain gauge. Now that is the tipping bucket that I showed before is an old system. Okay, we still use this because that is the ultimate measuring the actual measurement on ground. We still use those kind of system, but now we have a more advanced rainwater observation system. Okay, so we have the network of satellites, radars, automatic air stations. We can use the data from aircraft, surface stations, and which are surface rain gauge stations. That would help us to measure the precipitation on a global scale. So we'll have like a polar orbiting satellites, geostationary satellites that will provide us continuous and high resolution image of precipitation over large area. And also the weather radars, automatic stations, satellite sounding, these all provide real-time measurements of precipitation intensity and amount of atmospheric temperature, pressure, humidity, and other climatic information. So these measurements, so whatever we measure from the radar and satellites, we need to calibrate it, right? So the information that we get from these information, we need to calibrate with the ground stations. So it is important that all these measurements are calibrated and validated. So we'll talk about the calibration and validation uh, of the different models later in your assignment too as well. Now, these kind of systems provide accurate and timely information of rainfall patterns. If you look at uh, 30 years or even 20 years back, the system then and now is completely different. Now we have like uh, at least um, uh, at least a week or 10 days of very accurate weather prediction system. And that's all because of the advanced observation system. Now, let's say we have this rainfall station. So the measurement of the rainfall at the ground is the most accurate, obviously, right? So because that's the actual rainfall that you see. Uh, the measurement from the radar, that's the indirect measurement. It doesn't, or from the satellites, they are the indirect measurements only. They wouldn't provide us the exact precipitation on ground. If they provide uh, the um, the thickness of the cloud or um, some sort of indirect measurements only. Whereas these rain gauge stations provide the actual rainfall. Okay, that's what actually happened in those areas. So obviously, the rainfall stations are the most accurate ways of measuring the rainfall. But the problem is that we can't have too many rainfall stations. So if you look at this Yarra Basin in Victoria, it has like around 17 rainfall stations. Okay, so even in a very big basis, we can have a certain number of rainfall stations only. So now, if you want to find out how much how much rainfall occurred within this catchment basin, we need to find a way to convert these point rainfall into aerial precipitation. So how we can convert? Okay, so rainfall number 11 measures 30 millimeter of rainfall. Rainfall station number. So this measure 30. This may measure 20. This may measure 1, and this may measure 50. Okay, and so on. So how we can convert these different rainfall intensities at different locations to one uh, one precipitation that is representative of the entire basin, right? So there are different techniques for that, and for example, the most advanced is the kriging method. Okay. So this figure shows the kriging method. Kriging is a geostatistical technique, and that it is used to estimate the value of variable at an unobserved location. So these points are the observed location, and we want to find out what may be the rainfall at this point, what may be the rainfall at this point, what may be the rainfall at this point. So whole catchment is divided in number of small, um, what is called the grids. So number of small grids, and we want to find out what is the potential rainfall at these all different locations. So every 1 meter or every 5 meter we can calculate, and that's for that we can use the kriging technique. In the kriging techniques, we use a mathematical function called variogram, and the variogram is actually calculated by taking the square difference between the pairs of observation at different locations. So, what is the this point and this point, this point and this point, and also the unobserved location and the observed location. And from that we calculate the variogram and then use that for estimation of rainfall. So this kriging method can be used not only for rainfall, but for any interpolation of any climatic or any spatial data. Okay, this kriging method is obviously advanced, and it needs a computer uh, to calculate, but there are some other simple techniques as well. For example, arithmetic method, Thiesen's polygon method, and isohydral method, and we'll look at these simple techniques. So first one, the arithmetic main method. So this is very simple. It's just a number of we just sum the number of the rainfalls within the catchment. So if you have 17 stations within the catchment, then what we do, we take the average of all those stations. Okay, average rainfall of all the stations, and then we just assume that is the mean rainfall in the entire catchment. So let's say if the rainfall is so the average of all these different 17 rainfall stations is 50 millimeter, then once that is the depth of rainfall, right? And once we multiply with the catchment area, then we can calculate the volume of rainfall. Okay, so this is how we can convert the number of rainfalls data from number of rainfall stations to one average rainfall. Or uh, we can use another method which is called Thiesen's polygon method. So Thiesen's polygon method is better than this arithmetic method because regardless of where the stations are, the arithmetic method assumes they all are uniform and just average the value. Whereas Thesis polygon is a little bit more advanced. Here the catchment area is divided into number of polygons by the equidistance by the lines at equidistance between the pair of adjacent stations. So I'll show that in the next slide. And the third one is the isohydral method. So here we try to draw a contour. Okay, so let's say this is 30 millimeter rainfall, this is 20, and then we can draw like the 25 somewhere here, and 35 somewhere here, 30 here. We draw the contour and then we calculate what is the area. Okay, so that's the isohydral method. So let's see this an example. So you have the catchment here, and then you have the rainfall at different locations. So here the rainfall is 8.2, at this location 10.3, at 11.3, this rainfall station which are 17.4, and so on. Now what we want to do is we want to calculate what is the average rainfall in this catchment, right? So if it is arithmetic, you just sum them up, divided by the number of rainfall stations, you get the value. But if you want to use the Thiesen's polygon, first what you do is you join the stations. Okay, you join the stations by a line, straight line, and like this, and then you connect all the stations and draw some kind of triangles. Okay, so you try to make as equilateral triangle as possible. Okay, that's the first step. Connect all the stations with these lines. The next one is to draw the perpendicular. So for this, uh, between these two stations, uh, this is the connected line, and on that one you draw a perpendicular line. Okay, and you do the same for all these lines. You draw the perpendicular line, Okay, and this is the next perpendicular line, and this is the third perpendicular line for that particular triangle. And this way, we divide this, we calculate the affecting area of these particular rainfall stations. Okay, so for this area within this rainfall station, we assume the rainfall is 17.4. In this area, we assume the rainfall is 25.8. Similarly, in this area, we assume the rainfall will be 10.3. So obviously, it considers the distance between the rainfall stations, and it also considers the different rainfall stations, not like the arithmetic method. Okay, so the area for this 10.3 will be the line defined by this. Let me change the color. So this line, okay, so perpendicular bisector here, perpendicular bisector here, perpendicular bisector here, and perpendicular bisector here, up to the outside of the catchment. Okay, and this whole area belongs to 10.3. So now you calculate what is the area, and then you multiply with 10.3, and you get the volume of rainfall in this area. And similarly, you can calculate for all. So this is area, and third method is the isohydral method. Okay, so here again the same rainfall, but what we do now is draw the contour lines. So this is 8.2 meter, and this is 11. So you have like 9 meter here. Okay, uh, and you have this 10.3 and 20. So if you are drawing like every 5, so 8 and between 11 there is 10. So you try to draw the contour for every equal value. So you start with 0, 0, 5, 10, 15, 20, 25, like that. You can decide any. So you just draw the contour line. So this is the contour line of 10 meter. Okay, now you have this between 10 and 25, you have 15, 20, and 25, right? So between 10.3 and 25.8, there are three different points: 10, 10, 15, and 20. Similarly, here between 11 and 17, there is only one, which is 15, and then you draw this line with 15, right? And this way you draw a contour. So it's like in surveying. If you have already done surveying, you know how to draw the contour. Otherwise, yeah, so this contour is applicable in rainfall estimation as well. Okay, so to draw the rainfall of equal depth. So this contour means this area represents the rainfall of 15, and sorry, 10, and this is 10, and this is 15, right? So 10 and 15. So the whole area in between these 2 points represent the average of 10 and 15, which is 12.5 millimeter of rainfall. So obviously this is better than the isohydral method, which is just a geometric random geometry generation, whereas here you draw the contour based on the actual rainfall, and then you use that area. So these are three different techniques, and this is another example. You can have a look. So this is 4.9, 14.8, 10.5, 19.5. So different rainfall stations. You draw, you connect the lines, right? So you connect the lines and draw the triangles first, and then you just draw perpendicular for each line, and you get the area. So this area is for 10.5, whereas if you look at 20.5, it doesn't go to catchment outlet, so this area is for 20.5. So area bounded by these perpendicular bisectors give us the catchment area. So here for different stations, 14.8, 19.5, 4.9, all these different stations, we calculate what is the weighted area. Okay, so that is this actual area divided by the total area. So if you sum them up, it has to be 1. Okay, so that's the weight only. So if you get it, this in terms of like 5 hectare, this is 10 hectare and so on, and ultimately you divide each with the total area and you get the weighted area. And what is the weighted precipitation? Is the observed precipitation times the weight, that will give the weighted precipitation, and if you sum them up, then you will get the average precipitation of the area. So here the average precipitation is 6.2. If you have used this thesis polygon, obviously you will get different than the, sorry, if you have used this arithmetic method, you would have got different value than this one. And next one, for the same area, you have this isohydral method. You draw the contour lines. Okay, so you draw the contour lines, 5, 10-meter contour, 15-meter contour, 20-meter contour, and then you calculate what is the area. Okay, so greater than 20, what is the area? Greater than 10, what is the area? Greater than 5, what is the area? And we multiply with the precipitation and you get the average rainfall. And again, you can see it is different than the thesis polygon technique. Now, how many stations do we have in Australia? And then we can see there are so many stations around the world, sorry, around the country. And you can see where the population is higher. We have like larger concentration of the rainfall stations in the east coast, a little bit in the west coast, and also some in at the north. Now, if you want to design some water infrastructure in this area, then obviously you are going to use the rainfall data from that location. If you are going to use design something here, you are going to use the rainfall station data from that particular location. So if you are going to design a small infrastructure like a breeze, then probably you may get 1 or maximum 1 or 2, depending on where it is, rainfall stations, or maybe you may not have any rainfall station. For example, if you are going to design here, probably you don't get any. And even within this highly dense area, if you are going to design, for example, here maybe you don't have any rainfall station. So in that case, you need to get the data from the stations that are outside your catchment. Now let's talk about the losses. So when the rainfall occurs, before it reaches the ground, the water droplets are intercepted by buildings, intercepted by vegetations on leaves, branches, and trunks, and eventually it is evaporated back to the atmosphere. So this is called the interception loss. Uh, and this is also called the initial loss, and this can be estimated using empirical methods. So there are different empirical methods to estimate the empirical loss, right? Because our ultimate goal as a water resources engineer is to find out what is the runoff. So if the rainfall is this quantity, what is going to be the runoff? But from the rainfall to runoff, there are several losses we need to consider, and one of the loss is the interception loss by buildings or plants. Now another loss is called the depression loss. Depression is the portion of precipitation that is retained in the surface of ground. So you can see the surface is obviously not very smooth, and this does not contribute to the runoff. and it is also not infiltrating. You can see it is still there. It is not going inside the ground. It is also not contributing to the runoff. It is just staying there, and that initial loss is called depression loss. And we need to consider that also in our design. So how much depression loss that can be in our catchment. The next important parameter is evapotranspiration. And we know evapotranspiration has two components, evaporation and transpiration. So evaporation from the water bodies and transpiration from the ground. So evaporation is when water changes from liquid to gas, and it mixes in the temperature, and for this it requires energy, obviously, from sun, and also wind to transport the moisture laden air. So when it is heated, the air will have lots of moisture, but to uh, for the air to carry more for the sorry for the evaporation to happen further, then these air has to be moved away from that particular location, right? Otherwise it will have high humidity and there will be no evaporation. So we need to have wind to get the evaporation to happen. So energy and wind both are important. And transpiration is the evaporation of water which has been taken up by the roots. So roots take the water, and then it goes to up, and then through the leaves the water is evaporated. So evaporation, for civil engineering purpose, we combine the evaporation and transpiration together, and it is called evapotranspiration. Now, how we measure evaporation and evapotranspiration? For evaporation, we have like some kind of evaporation measurement instrument, which is called the pan evaporation. So we put um, uh, pan evaporation equipment at an open location, and it is defined by there's a standard. So you can't have like random pan out on the sun. So it has to be at a particular location, and then we measure the evaporation, how much water evaporated at that before and after. For the transpiration, we can use the lysimeter. Um, so pan evaporation measurement involves the measuring the amount of water that is lost from shallow open pan, and it has to be a standard size and placed at the standard defined location. And the lysimeter is actually a soil filled container with the plant, and we measure equipped with the weighing machine. Okay, so we equipped with the weighing machine, and then if you want to measure some other information like infiltration and others, we have these other sensors as well. And basically how much water is supplied and what is the change in the weight, and that will give us how much water is transpirated, and combinedly we can get evapotranspiration. Now there are different formula to calculate the evaporation and evapotranspiration. So let's look at the this empirical formula to estimate the daily evaporation. So E day equals to area of 0.291 times a to the power 0.05 U2, which is wind speed, which is 2 meters above the surface. Okay, so at every different level, what wind speed would be different. So for this equation, you just need the wind speed 2 meters above the surface. Okay, and A is the area of the water surface, ES is the saturated vapor pressure, and it depends on the temperature. So what is the temperature, that will define what is the saturated vapor pressure, and EA is the actual vapor pressure of the air above the water surface. So if you have these information, you can estimate what is the daily evaporation at that location. And if you want to calculate the evapotranspiration together, uh, this is an equation which is called Penman-Monteith equation. Highly used equation, and it is obviously a bit complex equation. It needs a lot of information, and it gives us the potential evapotranspiration, which is not the actual evaporation, actual evapotranspiration. So there is a difference between potential evapotranspiration and actual evapotranspiration. Potential evapotranspiration means if the water is available in full for to evaporate and for plants to respirate, right, transpirate. So that's the potential evapotranspiration. But even though there is a favorable conditions for evaporation, water may not be available. Maybe it is a dry location, then there will be no evapotranspiration, or much less than potential evapotranspiration. So the value it gives is the potential evapotranspiration, and we need to convert that in actual evapotranspiration later. So first, to calculate the potential evapotranspiration, you need these information like net radiation, soil heat flux, mean daily air temperature, wind speed, saturation vapor pressure, and actual vapor pressure, and slope of vapor pressure, psychrometric constant. So all these information you need, and most of these information you can get from climatic station. Okay, so there are rainfall stations and climatic stations. Climatic stations measure all this temperature, humidity, wind speed, all this information. Now let's talk about infiltration. Infiltration is the rate at which water seeps into the ground surface. When the rainfall occurs, when the rainfall occurs, then water seeps inside the ground, and the rate at which it enters the ground is called the infiltration. So when the rainfall occurs, the first thing it happens after the initial loss, water tries to infiltrate, right? And if it cannot infiltrate, then only the runoff, there will be surface runoff. Now, the rate of infiltration depends obviously in the precipitation rate. So if the precipitation rate is very high, then infiltration will also be high to its optimum maximum capacity. Type of ground surface, right? If it is impervious surface like this or pervious surface like this, it will depend. It will make a difference. Slope of ground surface, if it is a very slopy area, then um, the infiltration will be less than the mild slope area. And soil moisture condition, if the soil is already saturated like here, even though this is not an impervious area, because it is fully saturated, so rainfall or water cannot enter the soil. Okay, so all these factors affects the infiltration rate. Now, soil properties also affect the soil water movement. Now, so what are these properties? First is hydraulic conductivity of the soil. What is the capacity of the soil to transmit water? So different soil would have different ability to transmit water, and that is called the hydraulic conductivity of soil. For example, sandy soil, it has higher hydraulic conductivity, and the clay would have very small hydraulic conductivity. Okay, so different soil would have different hydraulic conductivity. And the next is the water retention characteristic, which means the ability to store and release the water. So some um, soil type can retain water a lot, and some can store but cannot release. For example, clay can store water but cannot release water, whereas gravel, it cannot store but it can easily release the water. So soil water retention characteristic is also important. Now, the actual rainfall, sorry, infiltration depends on soil, cover conditions, and rainfall intensity, obviously. And infiltration capacity means maximum rate as will at which infiltration could occur. Okay, even though you supply a lot of water, it cannot infiltrate after a certain point. That is called the infiltration capacity. Now, how we estimate infiltration? Obviously, infiltration depends on type of soil, initial soil moisture condition of soil, rainfall intensity, duration of rainfall, slope of ground, presence of vegetation, and to estimate rainfall, we have different techniques like constant rate method, exponential loss rate, physical model. So there are different techniques available depending on how accurate the results we need. Okay, when we need really accurate results, uh, then we may go for physical models, whereas we just need some kind of estimation, then we can use some empirical techniques. So this is one of the equation. It looks a little bit scary, but research equation of infiltration model. This is one of the most accurate method to estimate the infiltration in 3 dimensions. So once rainfall happens, how the moisture moves in x, y, and z direction. Okay, and soil may have different hydraulic conductivity in x direction, in y direction, and in z direction. So this model can model that scenario, and also the slope of the ground can also be incorporated here. Now, but for most of our engineering purpose, we don't need that complex model. Okay, basically for example, flood estimation, what we need is what is the amount of infiltration. Okay, we don't need how it moves x, y, z inside the ground. So if it is for agriculture, if it is for landslide, maybe those values would be important. But for flood estimation, that is not important. How the water moves inside the ground is not important. It's only important how much water infiltrates and what is the rainfall excess. Okay, so what is the amount of rainfall that is converting in terms of runoff or the flow or a flood. Okay, so that is only important to us for the flood estimation purpose. So we try to use some simple techniques for that, and one of the method is called phi index. The phi index is a measure of the infiltration capacity of soil. So not one particular soil, but the whole catchment. So again, it is empirical method, and it is uh, uh, average only. Okay, so obviously at if you are looking at the catchment scale, even in the very small catchment, there may be some impervious area, some pervious area, some vegetated area, a different kind of soil. So lots of complexities will be there, but we try to simplify that, and in an average, in the entire catchment, what is the infiltration capacity of that particular catchment, and that is the phi index of that location. So what we do is, after deducting all the losses, so first we deduct interception loss, depression loss, storage, the total remaining rainfall so can have two components. So either it will have the direct runoff or it will infiltrate in the ground, right? So once it reaches the ground surface after the losses, either it will seep inside the ground, which is infiltration, or it will produce it cannot seep inside the ground, and then it will flow downslope, okay, and create this direct runoff. So basically from this one we can say infiltration equals to available rainfall minus direct runoff. And we know rainfall can be measured, right? Uh, we can also measure the direct runoff, and once we deduct interception depression, then that means we can calculate what is the quantity of infiltration. Okay, so if you look at this figure here, this is y-axis, which gives us the rate or depth of per unit time, rate of infiltration or depth of infiltration, or a rate of rainfall or depth of rainfall per unit time. And in x-axis we have the period or time. Okay, and we can define this time in different periods. So from the rainfall starts, so this is the time where the rainfall starts, and there will be initial abstraction, that is accumulated loss up to the time of ponding. So there will be initial loss, okay, and then once that initial loss is satisfied, there is a in all the interception loss is satisfied. That means uh, all the water that can be retained on the leaves or buildings, it is already saturated. So whatever, if the rainfall is more than that, the leaves cannot hold it anymore, and water will drop down and then eventually reach soil surface. So after satisfying all those losses, then what happens? Water starts to infiltrate. So assuming there is a constant rainfall intensity, so initially there will be high infiltration, and the soil capacity will also reach its maximum point. So as you uh, increase the rainfall, so when the rainfall is constant and happening for a certain duration, after a point, the saturation limit of the soil will reach, and then after that there will be constant loss only. Okay, so there will be only constant loss, and that is the period 3. So you can divide this in 3 periods: period 1, period 2, and period 3. Okay, so period 1, losses, initial losses; period 2, infiltration starting at the maximum and then ultimately reaching this saturation infiltration, and then the infiltration being constant. Now let's see how we calculate the phi index uh, as an example. So let's say this is an rainfall. Okay, so in the y-axis we have the precipitation, and x-axis we have the time. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different time periods. So every hour, it can be every minute, whatever the time is. Okay, and we measure the rainfall. So initially rainfall is up to here, and in the next hour, let's say every hour, so first hour this much is rainfall, maybe x amount, p amount, and then a little bit higher rainfall, further larger rainfall, and the rainfall is up to here, and then again rainfall starts to drop. Okay, rainfall starts to drop, and then ultimately it goes to 0. So there is a rainfall for 10 hours, and we can measure that rainfall obviously, and we can also measure what is the surface runoff volume. Okay, so if it is the outlet of the catchment, we have the catchment here, and at the outlet of the catchment, it may be small catchment as car park, or it may be a big catchment with a big with a stream, right? It can be any catchment. So we measure the direct surface runoff, and we compare what is the actual precipitation amount and what is the surface runoff amount. Okay, so if there is after we deduct all the losses, whatever rainfall occurs eventually has to reach there, right? If not, then that amount is the rainfall infiltration. That's what we assume. So every time step what we do, so our 0, so what is the uh, r, what is the runoff? It has to be either 0, it has to be maximum of 0, so it means there is no negative runoff, or intensity of rainfall minus the phi index. Okay, so all these catchment have their own phi index value, and the intensity of rainfall minus phi index times the time, so millimeter per hour times the time, which is hour, will give us rainfall depth in millimeter. Okay, so this is how we calculate the direct runoff or rainfall excess. Okay, rainfall excess or the direct runoff is the amount of rainfall after deducting all the losses and all the infiltration. Now let's see this as an example. So here is the hourly rainfall depth that occurred during a storm event on 80 hectare area. Okay, so catchment area is 80 hectare. The volume of surface runoff from this storm was measured at 123 million liter. Okay, so you have the catchment area, and at the catchment outlet of the catchment, you measure for 10 hours or more. You measure, so and then you find out the total amount of water leaving the catchment after the rainfall is 123 milliliter. So what is the apparent pi index? So what is the infiltration rate that it is asking? Okay, now first we can find out what is the volume. 120 milliliter million liter, which is this many meter cube, and area is 80 hectare, and we can find out what is the depth of runoff is 153.75. Okay, so the runoff that you measure at the catchment outlet is basically 153.75 millimeter. So that's the depth. But what is the rainfall? Okay, so rainfall is different, right? So different times, different rainfall. So we know we want to find out uh, what is the phi index for that catchment. So this rainfall, okay, so this amount of rainfall minus this runoff should produce the phi index, okay, because all the values, all the remaining uh, rainfall seeps inside the ground. Now, same using the same equation for every hour, what you do, you just calculate what is the maximum of 0, which is the minimum, and I minus phi. Okay, what does that mean is that let's phi, we don't know the phi value at first. So if the phi value is, let's say 7.0 and rainfall is 8, right? So the basic concept is if the rainfall is less than the phi index, all the water will infiltrate. If the rainfall is more than phi index, the amount up to phi index value will infiltrate and the remaining value will be runoff. Okay, that's the fundamental concept. Because when the rainfall occurs, if there is a capacity to infiltrate, it will infiltrate, and that capacity is phi. If the rainfall is more than that capacity, then only there will be runoff, and that's why this is the value. So first time 0, the rainfall is 2.5, rainfall is 2.5 minus 5 because we don't know what is the phi value. Second, the rainfall is 7.5 and phi. Third, 17.5 minus phi, 47.5 minus phi, and so on. And minus 153, it has to be 0, right? So this is the amount of runoff. So this minus this has to be 153 because that is the runoff actually we have measured. Now what we do here, we just try to find the different values of phi. We play around with the value of phi. We can assume phi equals to 1 and see what is the, if you get 0 or not, and then you move in 2 and check 3, and ultimately if you get 7.75, you get exactly 0, and that means the phi index for that location for the scenario is 7.75 millimeter per hour. So what does that basically means that every rainfall, if the intensity of rainfall is more than 7.75, there will be runoff. The runoff amount is that intensity of rainfall minus 7.75. If the rainfall intensity is less than 7.75, then all the rainfall will seep inside the ground, infiltrate inside the ground, and there will be no runoff for that hour, okay, or for that time period. So this is another example for the phi index. Basin area is 200 hectare, direct runoff is 0.1 million meter cube, and direct runoff depth is 5 centimeter. Okay, now we want to find out what is the phi index. Okay, so time 0.5, the rainfall is given 0.5, 1, 1.5, 2, 2.5. We can do in the same way. We can also, I'm just trying to, so you can make a table and then also you can calculate. Okay, so it's the same method. The previous one is in equation form and this is in the tabular form. Now rainfall is given in terms of centimeter per hour, okay, 11,6,274 centimeter per hour. And what we do now is, again, we assume the value of phi. First we assume the value of phi equals 0.5. Okay, if the value of is 0.5 centimeter per hour, then what will be the phi value? So 11.5 minus 0.5, which is 10.5 centimeter per hour. And because this is the hourly, half an hourly, so you can say so every 0.5 hour, right? So every 0.5 hours, so that's why it is half hourly. So intensity you need to convert in hourly axis. So 10.5 divided by 2, which is 5.25 centimeter per hour. Okay, so 11 centimeter per hour, and then it becomes 5.25 centimeter per hour. So this 11 centimeter per hour for 0.55 hour. That's why you have to divide. Okay, so if it is every 1, 2, 3, 4 every hours, then you don't need this half. But if it is every 0.5 hour, so for half an hour the intensity is 11, and that's why you need to convert. So 5.25, 2.75, and then you calculate. Okay, so for second one is 6 minus 0.5, which is 5.5, and you divide by 2.75, and that will give you the runoff. And then for every hour, every half an hour you do, and then you calculate the sum. And the sum has to be, because it says the runoff is 5, right? So the runoff is 5, but if the phi index is 0.5, then runoff will be 13.75, which is not correct. So now you change the value. Phi index, you put the value as 2, do the same, and now it gives us 10, which is also not correct. Go to 4.5, it is nearly correct. 4.25, go to 4.6, close, and then 4.65, 5.03, which is very close to 5, and then we accept this is the right phi index. So phi index is 4.65. Okay, so this way we can calculate the phi index of that location. Now you can do the same. This is another example. I wouldn't explain it. So every half an hour the rainfall here is given in terms of millimeters. So it is important that you see if the rainfall is given in terms of millimeter or millimeter per hour. Okay, so if the rainfall is given in terms of millimeter for every half an hour, so 0.26 millimeter in half an hour, that means in 1 hour it would be 0.26 times 2. So intensity will be 0.26 times 2. Okay. So that is an important thing to consider if the rainfall is given in terms of depth or if the rainfall is given in terms of intensity. And then you can calculate the flow, you can calculate the flow volume and the catchment area. Okay. And so you can calculate the phi index of this problem as well. I'll not calculate, but I'll leave you to look at this information the same as previous ones. Next one is the percolation. So when water enters the soil after infiltration, it can move in different ways depending on soil characteristics and presence of vegetation. Water can move downward toward the soil due to gravity, or it can move laterally through the soil due to pore water pressure differences. As the water moves through the soil, it can be taken up by the roots of the plants and transferred back into the atmosphere. And this process helps to maintain the soil moisture and obviously support the plant growth. Alternatively, the water that moves downward can eventually reach the water table, and that is called the groundwater recharge. Okay, so water moves, infiltrates from the surface, and then it percolates and it goes down to the groundwater table and it recharges. And in some cases, water can also emerge as spring. So when it moves laterally, not 100% lateral, so maybe some downward slope and also the laterally. And in those cases, if there is a favorable geological formation is there, the groundwater can be discharged to the surface, and that what we see the emergence of springs at different locations. And it can also seep into river or lake as well. So the percolated water that is laterally moving that can provide water to the rivers during the dry period, also in the wet period, um, and lakes, and it helps to maintain their flow, maintain the water in lakes, and also maintain the water in river. Groundwater, when water reaches the water table, it moves as a groundwater and may emerge elsewhere as exfiltration. Okay, so there is difference between the um, groundwater. So if there is a surface, this is the surface, and this is the water table. So water table below that location, water is all fully saturated, and that uh, location is called the water table. Okay, so below that point, below that line, soil is fully saturated, whereas um, above that, water can be sometimes saturated and other times may not be saturated. And when we draw the water, we always draw the water from the saturated zone. Okay, that's where we get the largest quantity of water. And this unsaturated zone is basically for the trees uh, to capture the water and then use for their purpose. Surface runoff refers to the portion of precipitation that flows over the land surface into rivers, lakes, and other water bodies. Surface runoff can be measured using stream gauge, which record the volume of water flowing in a stream or river, or by measuring the change in water level in a pond or lake over the time. So water that neither evaporates nor infiltrates runs over the surface of the ground, and that's why they are called surface runoff. It may reach a channel and become part of the flood. It soaks into the ground at a drier location. It may flow down, and then when it finds the drier location, it may soak and seep inside the ground, or it can eventually evaporate. So to find out the quantity of runoff from rainfall, we can, if we need very crude estimation, we can use the coefficient called runoff coefficient, and that provides, okay, for a particular catchment, runoff coefficient is 30, 0.3. That means 30% of rainfall will reach the runoff. But that's very crude estimation, obviously. But if we need some quick estimation, we can calculate that runoff coefficient. Okay, we can use that runoff coefficient for quick estimation of runoff. Now let's talk about the data sources, where we get the different data that we need, the rainfall and evaporation and other climatic information. And here in Australia, Bureau of Meteorology website is the location where we need to go. Okay, so all the climatic information, rainfall estimation, measurements, the measurements of the stream flows, all information you can get from the Bureau of Meteorology website. Okay, so if the figure here, it gives us the total evaporation, okay, at different locations, and it is the annual. So you can get daily, you can get the monthly, different evaporation. For climatic data, you can go to climate data website, and then you select what you want. You want the rainfall, what kind of rainfall, and then you enter the location and you get the data. Okay. So so what you want, as mentioned, you just mentioned what is the information you are looking for, and then you go and select that particular location. You can select on the map, or if you know um, the location number, you can use that one as well. And this is an example of daily rainfall. You have rainfall. In some cases, we have rainfall for more than 100 years, daily rainfall. So it starts from 1887, and from that month we have like rainfall record. So more than 100 years of data are available for some locations, but not at all locations, obviously. So for discharge related data, you need to go for again Bureau of Meteorology website, but water data. So this gives us water data online, and then it gives us the measurement of the river flows at different stations. So from the map, you can find out if you have that, if you have the river stations for your project or not. And this is an example of river flow data. So this is the Barnett River, and from 1950 to 1978, it gives us the daily rainfall. Okay, and then you can see for this period probably there is no data. So you can expect that kind of things, especially if you are looking for the long-term rainfall and runoff and other data. Okay, so there could be missing data, and this is another big data, how to fill big research. So how to fill the missing data. Okay, so you can't just put some random values here. So there is a different technique, and lots of research has been done in this area, how to find out the missing information. So you use the other information from other locations, um, or rainfall and runoff of the different years, and then try to triangulate and then find the information.